I was born in 1976. I grew up here. This building is who I am. The patients, doctors, nurses, and staff, they truly are my family. Some thought I wouldn't make it, but great leaders fought for me. They believed that I could change Ottawa, Canada, even the world. And they were right. By the time I was 30, I'd saved thousands of lives, was recognized internationally, and had collaborated with over 40 countries. I've performed over 500 heart transplants, discovered the world's first genetic risk factor for heart disease, combined care, research, and education in one place, leading the way for innovation in heart disease throughout Canada and the world. I'm always thinking of the future and learning from the past. But through all this, I couldn't have done it, not without the people. The people here have taught me that through great loss can come great triumph, and that fear is never as strong as hope. I can't stop until there's a cure, and I will spend every second of my life trying to save yours. Some might say I've lived 1,000 lives, but I feel I'm just getting started.
This is quite a day for healthcare in Ottawa.
Doctors, nurses, volunteers, board members. It takes a community to build a place like this.
We will be able to perform more procedures, reducing wait lists in open heart surgery as well as in non-surgical procedures. The total of complex surgical and non-surgical interventions here will be over 12,000 a year.
Welcome to our home and your home from the bottom of our heart. Thank you very much.
I think it's enlightened.
It's an amazing.
Out of this world.
Magnificent.
Beautiful.
Incredible.
Amazing. Yeah.
It's like going to the Star Trek age because the technology here and all this is compared to before. So imagine how patients are going to feel when they're being treated here.
We're very pleased to have this new facility. It's going to be a tremendous improvement for our patients. Currently, they're in an area that's quite crowded. There's not a lot of space for their families when they come to visit, and it's certainly older. So now we're in this bright new facility. There's all sorts of space for them, and there's places for families. There's a terrace for patients who have to stay a long time. So it's going to be a huge improvement for the staff, but more importantly for all of the patients.
There's air everywhere, so there's nothing, and that's very important. And windows, because people after surgery, they get disoriented if they can't see outside. So there's windows in every place, and that's very, very important.
This is a moment we are waiting for the last 12 years. I mean, this is a brand new facility which is adjacent to our current facility that will include all the operating rooms, the intensive care beds, and which is serving 80% of our patients, because most of the things we do at the Heart Institute is very advanced cardiovascular care with open heart surgery, with high-tech medicine.
Beats Radio, scientists interviewing scientists.
Canada is a worldwide leader in science and innovation. However, our communities need to be more connected to current scientific research in order to drive the future of scientific innovation. So what steps can we take to more actively engage and connect our community with scientists and vice versa? Innovation and discovery are at the core of the current efforts of our government, but science sometimes gets slightly complicated to understand. At Beats Radio, we will tackle this by having young scientists and early career researchers interviewing scientists and innovators. By dissecting science in simple terms, this will allow our community to better understand the importance of science for our country. Stay tuned for the launch of our first radio podcast streamed from an actual lab.
Good morning, and thanks for tuning in to Beats Research Radio. My name is Hallie Arnott, and I am the Canadian Biomaterials Society Ottawa Student Chapter President and a graduate student at the University of Ottawa in Biomedical Engineering. Today I'm extremely excited to be here as your host on today's episode of Beats Research Radio podcast, streamed from an actual lab at the University of Ottawa's Heart Institute. So who are we and what are we doing here? So what Beats Research Radio is basically a way for us here at the lab to communicate scientific ideas, concepts to you, those in the community who are willing to learn from what we're doing here. What we're trying to do is get people to understand how scientific ideas get translated into the clinic and how we go from a scientific concept to experiments in the lab and then actually pushing that into the clinics. Today we have the pleasure of hearing from Drs Ouimet and Jean-Philippe St-Pierre, who are doctors here at the University of Ottawa. Before we start, I'd like to thank the University of Ottawa's Heart Institute, eLife, and the Canadian Biomaterials Society Ottawa Student Chapter, as well as the Beats research team here at the Heart Institute. So I'm now pleased to introduce you to Dr. Drs Ouimet, who is a researcher here at the University of Ottawa Heart Institute. She's an established scientist and researcher, and the director of the Cardiovascular Metabolism and Cell Biology Laboratory. She holds a Canadian Research Chair position in cardiovascular metabolism and in cell biology. Research lab focuses on molecular pathways and how modulating them can be used to treat cardiovascular diseases. So without anything else here, thanks for joining us today. How are you doing?
I'm doing great. Good morning, everyone. Thanks to Beats Radio for having me on. It's a true pleasure to be here with you today.
Awesome. So do you mind telling our listeners a little bit about your background, how you became a scientist, and how you found yourself working here in a lab at the Heart Institute?
Yeah, so I'm from Ottawa, and I guess my interest in science stems from high school. I went to high school at the Collège Catholique Samuel Genet, and I did a scientific concentration there, and I really loved all of the maths and physics and biology, chemistry, and I actually enrolled for an undergraduate degree at the University of Ottawa in electrical engineering because I really liked the math and the physics. But after a year, I found that I didn't like computer programming so much. So the C++ and Java programming classes were not for me. So I did a switch to biochemistry, and immediately I knew that was for me. So that was into my second year. I really loved the classes, the chemistry, the biology. And in my third year, I guess we were exposed to some scientific research articles, and when I would read them, I just was like fascinated with how scientists go about formulating hypotheses and designing experiments to test them. And the tools that they were using were so sophisticated to me, like the genetics and also the microscopy, how to look into a cell in real time and see what's going on at a microscopic level. And so I did a fourth-year honors project with a researcher here at the University of Ottawa Heart Institute, Dr. Yves Marcel, and that's when I was exposed to discovery science and health sciences and like the clinical aspect, and I would go to these seminars that are still ongoing, our Monday seminars where sometimes clinicians present, sometimes basic scientists present, and the Heart Institute is really a unique place where, you know, clinicians and basic scientists work together to kind of find cures for cardiovascular diseases. So it was an inspiring place. I went on to do my PhD here, and then afterwards I did postdoctoral training at New York University, and then I was recruited back 2 years ago to the University of Ottawa and started my lab here at the University of Ottawa Heart Institute. And it's a true pleasure to be back where it all started.
Awesome. So do you think you could tell us a little bit about your research that you do here at the lab on cholesterol and cardiovascular disease?
Yeah, so cholesterol is a very important molecule for life. Every single cell of your body needs some cholesterol, but we need the levels to be very tightly regulated. We can't have too little cholesterol or too much cholesterol. So the process of regulating cholesterol is called cholesterol homeostasis. So let's say a cell doesn't have enough cholesterol through the diet, for instance, then it can synthesize the cholesterol. And then if it has too much of it, so if you eat too much cholesterol, then the cells, if they have too much of it, can actually efflux it out. So to maintain this perfect cholesterol gradient. But as we know in our society, a common problem is high cholesterol levels. So this could be due to genetic susceptibility, so sometimes it's hereditary. You have a gene that makes you susceptible to high levels of cholesterol in the plasma. Sometimes it's due to insufficient exercise or not a healthy diet. For instance, if eating too much, I mean, it's hard in our society. We're pressed for time. We don't have time to exercise all the time. And then obviously there's a lot of, we're certainly not lacking any nutrients. So the result of persistent high cholesterol levels in the bloodstream would be an accumulation in the arteries. And so that is, you know, if the cholesterol that accumulates in plaques, and the plaques grow and grow and grow, and then if it becomes to a point where the cholesterol has accumulated and the plaques have grown so much that it occludes or blocks the artery, then that causes a heart attack. If it's an artery leading to the heart. If it's an artery leading to the brain, that causes a stroke. And so really what my research is focused on is how to reverse this accumulation of cholesterol in the plaques. And so currently on the drug market to treat patients, there are some cholesterol lowering drugs that people can take, and that will stop the plaques from progressing and bigger, but they won't necessarily shrink them or get rid of them. Exactly. And so we're interested in a cell process called autophagy and how this might be applied to degrade the lipids inside the atherosclerotic plaques in order to shrink them.
Oh wow, very cool. So you're basically trying to reverse this process, and once somebody has that plaque that has built up, taking these drugs won't help them, is kind of
it will help them for sure. It will definitely stop the process from going any further, but the plaques will still remain, and it's not an effective way to eliminate them. It won't. We actually are only just starting to be able to track the process in humans because so far imaging tools have been lagging behind, and so we are just now trying to find, you know, new biomarkers of the process as well as ways to look into that in humans, which is obviously not very obvious because when patients present to clinic, they already have, it's usually because they've had a clinical event. We don't know who has atherosclerosis. It's hard, and people are not screened for it. So in fact, fact, everybody has some degree of atherosclerosis. They found even in Egyptian mummies that they have evidence for atherosclerosis. So it's not only our society, and also in utero, like fetuses can have little plaques. So it's to some degree kind of normal. It's just over a lifetime, it just builds up to the point where it can be a clinically relevant. And so the process that we're studying, autophagy, is a process that every single cell does, and it's basically a degradative pathway that the cell uses to degrade maybe damaged organelles. For instance, mitochondria are the organelles of the cells that produce energy, and over time they can become damaged, and autophagy can then detect those damaged organelles and clear them and degrade them, and use their molecular components to build, let's say, other organelles or new mitochondria that will be functional. But the way that we're trying to use autophagy is to degrade the excess lipid that has built up in atherosclerotic plaques.
On the plaques, wow, very cool. So do you think that, so how would you explain this to somebody on the street, I guess, if you're just, if you have a couple of minutes and you're trying to explain your research and how it can be very beneficial for a clinic, and how pushing this type of research into the clinic as fast as possible is going to be helpful for these patients?
Yeah, so I guess it would just be saying that instead of just pressing pause on the disease, maybe we can reverse it. And that is the difference that we're trying to make, to find ways to eliminate it. So you go back to, kind of when you were younger, or in some cases, I mean, people they have a genetic predisposition, so they can't really,
so some symptoms that would be, or these people would present with plaque that has been built up over a long period of time, and it's gotten to a point where they've had a clinical event. Would they benefit by having like symptoms that they won't, that'll help them in their daily life, or is it something that they might not notice but is helping them?
I guess you could put it like, okay, so if you have your bathroom sink and it's clogged, what's the word in English? The conduit.
The pipe, I guess?
Yes, the pipe, thank you. If the pipe is has a bunch of gunk accumulated, and then it's narrower, and the flow, and then it backflows, and so that would be, obviously if you clean it with Drano, then you eliminate that. So it's a bit like that. I mean, it's not visible, but your heart is working harder if your arteries are narrower because of the plaque. So if you eliminate that, then your heart doesn't need to work as hard, and you can feel better. You wouldn't have maybe shortness of breath when you're hiking up a mountain, or so it's all invisible, and so it's really hard to.
Yeah, that's a great analogy, definitely, because sometimes if we don't know about these things, it's hard for us to really conceptualize, what it is, like visualizing what's actually happening in those arteries. But I guess explaining to somebody like your kitchen sink, it's be very difficult to use, and you might have long-term damage there if you don't clean it right away. So that's I think that's a great analogy there. So do you think you could tell us what I think foam cells are something that you look into? So
yes,
what are these foam cells, and what do they have? I guess they have a role in inflammation, and the development and progression of these cardiovascular diseases. Do you mind telling our listeners a little bit about
of course.
those?
Yeah. So foam cells are, if you were to take a magnifying glass into atherosclerotic plaques, what you would see is a bunch of cells, and inside of the cells, you would see kind of like all these little drops of oil, essentially. And then all of the little drops of oil are in fact each a lipid droplet, so that's the organelle that the lipid is stored in. And so because of all these little drops of oil, it makes it look kind of soapy or foamy, and that's why we call them foam cells, because of their appearance, because of all of the lipid that they've accumulated. So the reason that these cells are there is because when the high cholesterol levels in the bloodstream cause the cholesterol to accumulate inside the artery wall, it actually becomes modified, that cholesterol, and then it's detected by the body as not normal. And so these immune cells come in and they try to clear it away. And you know, initially that's very good because they come in and they digest the lipid, and then they try to efflux it out. But at some point there's just so much lipid that they become overwhelmed, and when they become foam cells, then they're kind of stuck there, and they're trying to recruit other cells and to get help. To help out, right. And the signal that does that are inflammatory signals. Okay. Inflammation can be good. For instance, if you cut yourself, you have a wound, and then you have inflammation to heal. You need the cells of the body to detect the wound and say, come help, and then recruit the help that's needed, and then promote the wound healing. And if you have a cold or a flu, then you fight that infection, and inflammation can be pro-resolving, right? But in the case of atherosclerosis, it's a chronic silent inflammation. It's sterile. There's no infection. It's from within, and it's the cells that are calling for help, and then other cells come in, and they also become foam cells, and so then they call for more help, and then more cells come in and become foamy, and then you just have the plaques that grow and grow and grow, and the inflammation that drives these plaques to grow. And in fact, there was a recent clinical trial that showed that if you block this inflammation, then you can reduce the risk of patients to have cardiovascular disease events. And so there's really a two-pronged sort of cause to atherosclerosis. One is the lipid accumulation that we need to deal with, so try to degrade the lipids, get rid of them, eliminate them from the body. And two is the inflammation, so we need to also find ways to mitigate that. And so foam cells, yes, they're good in the sense that they've come and they're trying to degrade the lipid, right? But then they're pro-inflammatory and they're driving the process. So it's what we would like to do in our lab with a team of people, talented trainees that are working on this, is to really understand how we could possibly tag the little oil droplets, the lipid droplets, for degradation by autophagy. Because I told you autophagy is a degradation system. So these cells are unable to digest the lipid that they've ingested. And so if we could say, okay, well, come and degrade this and enhance that digestion of the lipid, then maybe they could efflux more, and that would help resolve. Yeah, and the inflammation will be dampened, and so it would be like a two-hit thing.
Very, very cool. Awesome. So you said some trainees are there. Do you have PhD and masters as well as undergraduate students working in your lab?
Yeah, so there's Sabrina Rabichaud that started as an undergraduate student, and now she's into her master's, and she wants to transfer into the PhD in the new year, and she's working on elucidating the role of autophagy in immunometabolism, so driving inflammatory processes in these foam cells. And there's also Garrett Fairman, who is a master's student in the lab, and he also wants to transfer to his PhD in the new year, and they're both doing great. And he is looking at the genetic requirements of the lipophagy process, and we have a new undergraduate student, Amrit, that just started, and also some research technicians that are really driving these projects forward.
Yeah, great group of students. You are a Canada Research Chair, so do you mind telling our listeners what that means and what it means to you, especially as a female scientist, what that means and what a Canada Research Chair is?
Well, a Canada Research Chair is an award to promote research in Canada. It's a government award to try to recruit scientists that are leaders internationally and nationally in the field. And there are two types of Canada Research Chair. There is a Tier 1 and a Tier 2. So Tier 1 Canada Research Chairs are for established leading researchers in the field, and the Tier 2 Canada Research Chairs are for promising potential leaders, like future leaders. So then I was recruited as a Tier 2. And so I guess the hope for me is that I establish some relationships and collaborations with other leading researchers in Canada and around the world, and really kind of have a good research program. And there are some funds associated with the award that help really launch your research program. So it's a huge advantage in terms of this initial fund. So it's a 5-year award initially, and it's renewable for another term, possibly. And so that really, really helps a young investigator obviously build their research program. And also, very oftentimes, Canada Research Chair will be encouraged to apply for CFI funding, which is equipment funding, and then that can help secure some new equipment in the institute that the researcher might need. So, for instance, the Seahorse instrument that was the first Seahorse instrument at the Heart Institute, and I was able to acquire that through my CRC and CFI funding. So, it means a lot in terms of getting the best technology in order to do the research here.
Exactly. So. You said that you're able to, with this chair, you're able to develop collaborations and, talk to a lot of people in the field. Have you felt that this chair position has given you that opportunity, and do you feel like you've really been able to reach out, or people have reached out to you for collaborative opportunities?
Absolutely. I think that the more time that we're in the lab writing research grants and applying for funding is less time that we have in order to travel around and present our research findings at conferences. Conferences do take a lot of time, and I'm involved in some of the American Heart Association committees, so the Early Career Committee and the Women's Leadership Committee, and I have to attend the HA and ATVB, so that's twice a year for a few years, several years. And so if I didn't have the funds to be doing the research, then I would have to be like in my office writing these grants. And so all of that just takes that financial stress kind of away and allows me to go out and do the best that I can. And then, at these conferences, you learn about the cutting edge research. You're always forming new relationships. And so definitely it's had a big impact on my research for sure.
Awesome. So do you mind telling us a little bit of a non-science, route we're taking here? So when you're not a scientist walking into the Heart Institute doing work every day, or being at a conference, what do you like to do in your spare time?
Yes, okay, the spare time.
Things that your lab does.
Yes. So I enjoy art a lot, and I guess that might be part of the reason why I love microscopy so much. And I really like making figures of papers, for sure. It's like a bit of an art thing. I'm like, oh, what color bars should I, there's something choices. Yes, but I do like art, so I like to go to art shows, and I like to make art or paint things in my house, like refurbished furniture and things like that. But I'm not super good, but I do enjoy doing those things, and I like the outdoors, hiking and traveling, and I have a young daughter. She's 1.5 years now, so she takes up a lot of time. So I go to the experimental farm and look at animals and things like that. But I enjoy spending time with her. So and cooking and eating and everything.
Oh, good. So just before we take off here, what are some of the next steps of your lab? Just briefly, a couple of things that are in the future for for your lab and
Yeah.
research?
So we are completing, so we had done in collaboration with Danielle Figui's lab at the University of Ottawa. So we'd done some proteomics work to identify some lipid droplet proteins that might potentially regulate the lipophagy process. So we're currently validating these functionally with some high throughput efflux screens. So this is something that we're aiming to complete in the next month or so. So that's one of the big projects in the lab that we're close to completing. So that's very exciting. And then also Garrett, who I told you about, has done a mutant array of yeast. So there's 4,000 yeast, each lacking different genes, and we're going to be doing like a high throughput screen to find genetic requirements of the process. So it's very exciting. I think in the next few months we'll have a really good idea of some of the proteins that regulate the breakdown of lipid droplets, and so then we look forward to testing these in some atherosclerosis models.
Oh, very, very cool. So thank you to all of our listeners for this first part of the Beats Research Radio episode today. I'd like to thank Dr. Ouimet for being here today with us. Yes, so we'll see you later with Dr. Jean-Philippe St-Pierre, who will be speaking to us about his research. Yes.
Thank you. Bye.
I was born in 1976. I grew up here. This building is who I am. The patients, doctors, nurses, and staff, they truly are my family. Some thought I wouldn't make it, but great leaders fought for me. They believed that I could change Ottawa, Canada, even the world. And they were right. By the time I was 30, I'd saved thousands of lives, was recognized internationally, and had collaborated with over 40 countries. I've performed over 500 heart transplants, discovered the world's first genetic risk factor for heart disease, combined care, research, and education in one place, leading the way for innovation in heart disease throughout Canada and the world. I'm always thinking of the future and learning from the past. But through all this, I couldn't have done it, not without the people. The people here have taught me that through great loss can come great triumph, and that fear is never as strong as hope. I can't stop until there's a cure, and I will spend every second of my life trying to save yours. Some might say I've lived 1,000 lives, but I feel I'm just getting started.
This is quite a day. Quite a day for healthcare in Ottawa.
Doctors, nurses, volunteers, board members. It takes a community to build a place like this.
We will be able to perform more procedures, reducing waitlist in open heart surgery as well as in non-surgical procedures. The total of complex surgical and non-surgical interventions here will be over 12,000 a year.
Welcome to our home and your home from the bottom of our heart. Thank you very much.
I think it's enlightened.
It's an amazing.
Out of this world.
Magnificent.
Beautiful.
Incredible.
Amazing. Yeah.
It's like going to the Star Trek age because the technology here and all this is compared to before. So imagine how patients are going to feel when they're being treated here.
We're very pleased to have this new facility. It's going to be a tremendous improvement for our patients. Currently, they're in an area that's quite crowded. There's not a lot of space for their families when they come to visit, and it's certainly older. So now we're in this bright new facility. There's all sorts of space for them, and there's places for families. There's a terrace for patients who have to stay a long time. So it's going to be a huge improvement for the staff, but more importantly for all of the patients.
There's air everywhere, so there's nothing, and that's very important. And windows, because people after surgery, they get disoriented if they can't see outside. So there's windows in every place, and that's very, very important.
This is a moment we are waiting for the last 12 years. I mean, this is a brand new facility which is adjacent to our current facility that will include all the operating rooms, the intensive care beds, and which is serving 80% of our patients, because most of the things we do at the Heart Institute is very advanced cardiovascular care with open heart surgery, with high-tech medicine.
Beats Radio, scientists interviewing scientists. Canada is a worldwide leader in science and innovation. However, our communities need to be more connected to current scientific research in order to drive the future of scientific innovation. So what steps can we take to more actively engage and connect our community with scientists and vice versa? Innovation and discovery are at the core of the current efforts of our government, but science sometimes gets slightly complicated to understand. At Beats Radio, we will tackle this by having young scientists and early career researchers interviewing scientists and innovators. By dissecting science in simple terms, this will allow our community to better understand the importance of science for our country. Stay tuned for the launch of our first radio podcast streamed from an actual lab.
Good morning again and welcome back to Beats Research Radio. My name is Hallie Arnott and today we are here to tell you guys about stuff we do in the lab and how that makes its way to the clinic. And we speak to researchers who are doing the work in the lab in translational research. So today I now have sitting with me Dr. Jean-Philippe St-Pierre, who is a professor and researcher at the University of Ottawa in the Department of Chemical and Biological Engineering. The St-Pierre Biomaterials Lab focuses on the development of novel biomaterials for applications in tissue regeneration and the fabrication of 3D tissue models that can be used in translational medicine. So here we are speaking to Dr. St-Pierre, and I'm pleased to introduce him to you today. So thank you for being with us. Do you mind telling us a little bit about yourself and how you became a scientist and how you found yourself at the University of Ottawa with the Department of Chemical Engineering?
Absolutely. Well, so I'm from the region. I'm from Elmer, so just across the river. And I actually did my undergrad year a long, long time ago.
In science or
in biotechnology, which is a double program where so you get one degree in chemical engineering, which is the department I'm working in now, and another degree in biochemistry. And so you do both science and engineering. And so how I got involved in research is a little bit by chance, because really when I was halfway through this program, which is quite a long program, you're doing 2 degrees at the same time, I was quite done with school. I was ready to find a job and move on. But I was part of the co-op program. We talked about that a little earlier. And I had an experience in research with the National Research Council of Canada. And essentially I walked in, didn't really know what it would be. They told me, well, we have this great idea to make a material It's very easy, just like making bread, but with a few differences. Like instead of using flour, we use metal powder. But anyways, but it just doesn't work. So fix it. And so I started on this, and by the end of my first term there, I had something that was just about working. And so we made great progress, and I was hooked on research. So I completely changed my career plan, and I got involved with research.
Okay, so this was a co-op that you did in your undergrad degree at towards the end?
I think it was my second one, so it would have been in third year. And I went back there for a third one after that.
Okay, yeah. I also did the co-op program, and I had the same kind of experience with research. So that's great that other people did too. So in your lab, can you tell us about how you kind of came into now the research that you're doing from the material science that you did at the Research Council and to what you're doing in your lab now?
So obviously initially it was a materials project. So we were developing porous materials for a number of applications. And by the end of my undergrad, by the end of my co-op terms, they asked me if I wanted to do a master's degree. And said, well, if so, which application do you want to take this project? And one of the options was biomaterials. That's how I got involved in biomaterials research. So I did a master's at McGill on the same material, characterizing the cell response to that material. And then by the end of it, I liked the idea, so it was a metal implant, so I liked the idea of being able to replace damaged tissues. But I was just thinking, well, it would be more interesting, in my opinion, if we could regenerate the tissue rather than replace it. And so I got involved in tissue engineering. I went to do a PhD at the University of Toronto. And again, in the same, so the implant was for orthopedic applications, so repairing damaged joints. And I kept with that research, but with the idea of regenerating the articular cartilage surface, which gets damaged during disease, during arthritis. And then I moved from there to the UK for a postdoctoral fellowship with one of the big biomaterials lab in the world, and was lucky enough then to get this opportunity to come back home and work at the University of Ottawa.
So we're going to come back to that lab a little later on, but before we move any further, do you think you could tell our listeners a little bit about tissue engineering and as a whole what it is?
Sure. So the overall goal of tissue engineering is to actually create new tissues outside the body that can then be transplanted to replace damaged or diseased tissues in our body, or to try and create this regenerative process in the body directly. And so obviously what you need to accomplish this is you need cells that can regenerate the tissue. So they're essentially your little workers who are going to deposit new tissue in the body or outside the body. And so what we do in tissue engineering is that we use materials, which we call biomaterials, to essentially guide this process. It's kind of housing those cells and providing them with the right signals, messages to guide them along the way of the regenerative process. So obviously these materials will be designed to include these biological and mechanical messages to the cell. And so essentially the idea is that you want your material to also eventually degrade over time, so that as the new tissue is being deposited, the material goes away and eventually you're left with just a new tissue without any appearance of intervention. That's the overall arching goal.
So kind of like building a building, you have the workers and you have some scaffolding, and then once they all leave, everything is looking how you want it to.
Exactly.
Kind of a little analogy.
But I guess you also design your scaffold in such a way that there's all of the directions on how to build the tissue, and that's where it gets difficult, because obviously those signals might be different in one location of the tissue from the other. They might change over time, and so you need to integrate that complexity variety in your materials.
So a big part is trying to create these materials as closely, as a closest replica to what is in the body.
That's one view of it.
Right.
There are other views. Some people think that you just need to provide a minimal environment and the cells will know what to do on their own.
Right.
I think, both approaches have yielded some successful results.
Yeah.
So I'm not sure that you necessarily need to match your material as closely as possible, even though this is one strategy we're following in the lab.
Definitely. There's everything's progressing, evolving, and there's lots of solutions to lots of problems. So do you mind narrowing in on the cartilage repair that you're working on in your lab and the tissue regeneration that's involved in that?
Absolutely. So the main focus of our group is to try and develop new technologies to help regenerate damaged cartilage.
Okay.
And so the idea is that cartilage gets injured, either because of sports injuries, and it can also get diseased. And so there's a number of factors that can change how the cells behave. And so what we have to understand about cartilage is that over the span of a year, if we take the knee, for example, about 1 million times will there be force applied to your tissue. That's quite a bit of load that the tissue needs to take in. And so the way that the tissue manages that is that it constantly breaks down older parts of the tissue and replaces them with new building blocks.
Okay.
We call this remodeling. And what happens with disease, with arthritis, is that some factor influences that balance, so that suddenly you have just a little bit more degradation than you have new tissue synthesis. And so over a period of decades, or at least years, your articular cartilage layer gets degenerated, and so you lose it. So eventually you get bone rubbing on bone, and that's very painful for a patient. And so essentially this is what we're working with, is this idea that we need to intervene either early on with small damage that could lead to that degeneration, or at a later step when the tissue is completely damaged. So essentially what we're trying to do is twofold. So the first part is we're targeting the tissues that are already damaged, and the damage is quite advanced, and this is what we've been talking about, the tissue engineering aspect. And so what we're trying to do is, as you mentioned, we're trying to recreate the normal environment of cells in cartilage. And there's this special matrix, this special tissue around the cells that instructs its responses. And so we create materials that encapsulate our cells with the ability to regenerate cartilage. And then we try to modify this environment so as to either stimulate more formation of new tissue, or inhibit the degradation of the tissue. So to try and recreate that balance between the two events. Obviously, if you have a little bit of damage, you probably want a little bit more regeneration, then degeneration. Balance might not be sufficient. And so this is obviously a major axis of research in my lab. And of course, we're also trying to target some of the elements of the disease and take them out of the equation. I'll give one example. So for example, in the body and in cartilage, there is reactive oxygen species, and one name that people will know is hydrogen peroxide. And a certain level of these reactive oxygen species is necessary for cell function. But in OA, in osteoarthritis, these levels go way up, and that can damage the cells. So what we might do is then add antioxidants to our material so that we lower the levels of these reactive oxygen species, in addition to trying to stimulate tissue regeneration.
Yeah, so there's a lot that you need to look into. So there's, looking at, how the damage actually occurs and then applying that to your biomaterials. So there's a lot of different aspects that you need to focus on, which is interesting. Do you find that, you have to create a lot of interdisciplinary collaborations in order to come to the, create a full project and, get all the correct information?
Absolutely, yeah. I mean, we have obviously engineers in the lab, but we also need biologists and chemists to be able to modify our base materials with which we build these scaffolds, these hydrogels, and of course we need to be in contact with clinicians to know if the materials we're thinking about can be translated into clinic, and if they would be receptive to a certain approach in terms of how it requires them to modify their surgeries. I was going to say another aspect of the research that we're doing is completely different in that one of the issues with arthritis is that there's currently no cure. And that's a problem because we can't stop the disease from progressing. And so one of the reasons why that is not because there's no candidate drugs for stopping the disease, but it's because when you insert or you inject a drug in the joint to try and slow the progression of disease, it gets cleared from the joint really, really quickly, so within hours. And so trying to retain a drug in a certain location is an amazing problem for a biomaterial scientist. This is perfectly suited to what we do. So what we've been doing recently is trying to develop these very small particles, which are going to be drug carriers. And obviously, what we want is for these particles to be small enough and functionalized or modified in a way that they will find their way through the small pores of cartilage tissue and essentially bind to some component of the cartilage tissue so that they stay in the tissue rather than being cleared from joint. And then they can locally deliver a drug over a very long time rather than requiring someone to come back regularly for injections.
Okay, yeah, definitely. So that type of research, it's almost self-explanatory how translational it is and how impactful it can be for these patients who suffer from osteoarthritis and different types of degenerative diseases. So it's kind of even hard to ask you how your research could impact the community because it just completely will. So how do you think, or what are some of the obstacles that you see in translating this type of technology and biomaterial into a clinic? Because it does take quite a long period of time.
Well, so what we've been doing, as you mentioned, the process of translation is a very long process. And so what we've been doing is we've been trying to target clinical strategies that already exist. So for cartilage tissue engineering, already cells with cartilage repair abilities are injected in the sites of defects on your cartilage to try and regenerate the tissue. So what we're trying to do is simply improve on this particular intervention by using materials to help guide the cells in the process of regeneration. So that's one element to try and make the time between where we are now in our research and when we can impact clinic a little shorter. Having said that, another thing that we're doing which might have an impact sooner is that we're also starting to use our engineered tissues, so the tissues that we grow in the lab, as models for parts of or elements of the disease. So we can use these tissues and we can impose some chemical or mechanical insult on these tissues and observe what's happening. And so that gives us a little bit of an idea of how the disease progresses, because we really don't understand how arthritis develops at the molecular level. And that's important because it allows to instruct clinician decisions. So what we learn with these models, which can't be easily tested in animals because there's quite a number of differences between animals and human responses. So what we learn can be used by clinicians to make the right decisions, but it can also be used by biologists. And so if the biologists know which mechanisms are involved in progression of the disease and which molecules are involved, then they can develop drugs to target these molecules specifically.
Okay, and that model will be used to test them and just see how.
Absolutely.
Okay, and I guess it could also be personalized medicine as well, because, you know, if you were to, I guess, they must do some sort of test, but if you were to actually use like a person's, you know, if a piece of cartilage, or if, you know, you take a piece that's been degenerated, then they can test using the model, which would be
absolutely
very cool.
and there's new technologies which would allow the ability to take cells from someone's skin and then regenerating
stem cells, for example.
Yeah, you could differentiate them so that they can build new cartilage and then have cartilage made from the person's own cell, so that you can verify what type of intervention might work.
Best for them, right? That's very interesting. So going back to, I guess, your postdoc at Imperial College in London, and the biomaterials lab that you were working in there. Do you mind telling our listeners about that experience? Because I understand that it was a very world-class lab to work in. So.
Yeah, well, so I was very lucky to get this opportunity, and I would certainly recommend to anyone who's in research and has this opportunity to go abroad and work in a lab outside of Canada, to just jump on that opportunity, because you'll live life experiences and scientific experiences that are quite unique. In terms of the lab that I was working in, it's a very big lab. We were about, at its peak, 70 to 80 people in the lab, which is as big as the entire department I'm working in terms of grad students. And the students and the postdocs that were there were coming from everywhere in the world. So it was a unique opportunity to meet people from different backgrounds, so chemists, engineers, physicists, and biologists working together to solve some of the key problems in the field. And so for that opportunity to build your network and to meet really motivated young researchers, it was absolutely unique. Yeah.
Very, very cool. So one last question before you take off. What do you do when you're not being a researcher and Colonel Bai at the University of Ottawa? What do you do in your spare time?
Well, it's changed a little bit recently. Okay. My wife and I had a little girl. She's 17 months old. So I think
takes a chunk of time.
And building a lab requires a lot of time. So I try to take as much of my extra time and spend it with my family. I used to be a runner and a soccer player. I think I've had too many injuries to push the soccer again, but I've been trying to get back into running a little bit. This is something that I really enjoy, and I can't do it as much as before, but I'm still trying to do a little bit.
Okay, well, thank you for joining us, Dr. St-Pierre.
My pleasure.
And to our viewers, thank you for tuning in today. This is Beats Research Radio signing off for this week, and we'll catch you next week at the same time.